All right, speaking of the drop date, your exam scores, I literally have one test left to grade. So as soon as we finish this class, I'm going to pop upstairs, grade that one, and post your grade. So you should expect it within 15 to 20 minutes after we finish up here, maximum. I can say that of the, I think 20 of the 21 that I've managed to get finished, the scores are ranging from around a 55 to a 101, with the average somewhere in probably the low to mid 70s, just completely based on me looking at them, no math whatsoever. So I could be wrong, but that's what I feel like it's going to be. So we are going to finish our chapter on frequency response today by looking at Cascode amplifiers, and then very briefly at differential amplifiers. And I mean very briefly because if you look at the half circuit, it's a common emitter amplifier, so why do we need to do it again? So with that in mind, we, as per usual, are going to be looking at the Mosfet variation of this guy. One thing that I do want to point out is that I couldn't find a single example of a Cascode amplifier with a low frequency bias circuit, or I guess a bias circuit that would impact its low frequency gain. So we're just not going to cover it, because if we did anything, it would be biasing the transistors with a voltage divider network to set the DC operating point, and then applying an input capacitance to separate the AC input signal from that DC operating point, which would look like the exact same input stage that we've done on every other amplifier. So I don't really see the point in revisiting that again. So at high frequencies, our Cascode amplifier is going to look something like this. That'll work. So let's see. Here we're going to have some capacitance CGD2, meaning that this is transistor M2. Here we are going to have a capacitance CGS1. I'm going to apply a DC bias voltage, V bias, to the gate of transistor M2. Let's see. This is our capacitance CDB2. This is our output pin where we measure our output voltage. Additionally, we are going to have a source body capacitance. So let's call this guy CSB2. Down here is where we've got transistor M1. So we will have some CGD1 that goes here. Some CGS1 that goes here. We have some signal resistance, goes here. Here is where our input signal is applied. Our source for transistor M1 is grounded, which means we have this guy CSB1 right here that does absolutely nothing. And lastly, we're going to have a capacitance here, CDB1. So this arguably looks pretty scary, right? But we can make a couple of observations. The first of which is obviously VDD is going to be an AC ground, and V bias is going to be an AC ground. So what that does for us is it puts CGD2 in parallel with CDB2. CGS1 will be in parallel with CSB2 and CDB1. We have this feedback capacitance CGD1 that's going to make this difficult to deal with directly. And then we have this guy CGS2 is down to ground. Yes, Mr. Goldsmith.
The top CGS1 be CGS2?
Yes, thank you. Thank you very much. Yes. So this is transistor M2, so all of its capacitors should have a subscript of 2. Thank you for catching that. That would have been rather confusing in a couple of minutes. So I can draw a small signal model for this guy. We're first going to analyze it directly. And so my small signal model is going to look like this. Where we are ignoring any channel length modulation effects. And I'm going to call this capacitance C out, which again is just CGD2 plus CDB2. And here's where I'm taking my output voltage. Then I have to deal with my lower transistor. GM1, VGS1. I'm going to call this capacitance CY, where CY is CDB1 plus CSB2 plus CGS2. Here is R sig. Here's VN. Here's my capacitor, CGS1, over which the voltage drop VGS1 occurs. And here is my capacitance, CGD1. And down here is ground. So I am going to label this node as X, this node as Y, and I'm going to wind up having to do KCL at node X, node Y, and the output node in order to develop a transfer function for this thing. So let's start at node X. We would have Vx minus Vn divided by R sig plus S CGS1 Vx, because we can see by inspection that VGS1 is exactly equal to Cx. Let's see, then we're going to have plus S CGD1 Vx minus Vy is equal to 0. And so I'll go ahead and start working on some algebra here. Vx over R sig plus S CGS1 Vx plus S CGD1 Vx minus S CGD1 Vy is equal to Vn over R sig. And we can thus simplify that as Vn over R sig is equal to 1 over R sig plus S CGD1 plus CGS1 all times Vx minus S CGD1 Vy. So we have our input in terms of our nodal voltage at X and our nodal voltage at Y. Now let's go ahead and do KCL at node Y. Okay, so at node Y, we have the current flowing to the left through CGD1, the current flowing down through our dependent current source, the current flowing to the right through capacitor CY, and then the current flowing up through our other dependent source. So we're going to have 4 terms. So that's going to be S CGD1 Vy minus Vx plus GM1 Vx, again, because VGS is, VGS1, is exactly equal to Vx plus S CY Vy. And then if we look up here, we can see that VGS2 is exactly equal to negative Vy by inspection, right? The negative polarity terminal of VGS2 is connected to node Y, positive polarity terminal is connected to ground, so Vy is equal to negative VGS2. So when we do our Kirchhoff's current law bit here, the current that's flowing out is negative GM VGS2, which is negative GM times negative Vy, or positive GM Vy. Is equal to 0. And then let's do a little bit of algebra again. So we're going to have S CGD1 Vy minus S CGD1 Vx plus VMVx plus S CY Vy plus GM2 Vy. And it looks like I'm miswriting the 2 directly above it, so I corrected that. Is equal to 0. Grouping like terms together, we have GM2 plus S CGD1 plus CY times Vy is equal to negative GM1 plus S CGD1 Vx. Excuse me, there shouldn't be another equal sign there. And from that, I can rewrite this guy as Vx is equal to GM2 plus S CGD1 plus cy, all divided by negative gm1 plus s cgd1 times vy. And if I substitute this expression into, let's call this guy 2 and this guy 1, I can see pretty easily that now I'm going to have Vn in terms of only Vy. So 2 into 1 yields Vn over R sig is equal to 1 over R sig plus S CGS1 plus CGD1 times GM2 plus S CGD1 plus CY, all divided by negative GM1 plus SCGD1, all times VY minus SC, go away, go away. Collapse. No, that's not at all. Clear everything and go away. There we go. CGD 1 VY. And now I'm going to multiply that right-handmost term by a factor of negative GM1 plus SCGD1 over negative GM1 plus SCGD1 to be able to combine everything to one horrifying looking numerator, as per usual. And we'll go from there in a second, okay? So with that in mind, this is going to look like R sig to the minus 1 plus S CGS1 plus CGD1 times GM2 plus S CGD1 plus CY minus SCGD1 times negative GM1 plus SCGD1. Close this thing. All over negative GM1 plus SCGD1. Okay, so for my next step, and this is going to be both maybe more and less terrifying at the same time because it does involve a couple of simplifications. What I'm going to do is I'm going to multiply both sides by R sig to clear that so that I'll just have Vn on the left-hand side. And I'm going to wind up foiling out everything and taking some terms away because there's going to be some cancellation. Hopefully it's fairly obvious to see here that, for instance, I'm going to have S times CGD1 times S times CGD1 is going to give me S squared CGD1 squared. And over here, I'm going to have minus SCGD1 times SCGD1 is going to give me a minus S squared CGD1. So a couple of things are going to cancel out. My result is this. Vn is equal to S squared times R sig times CGS1 CGD1 plus CGS1 CY plus CGD1 CY plus S times CGD1 plus CY plus GM2 R sig CGS1 plus CGD1. Oh, I'm running out of room. Plus GM1 CGD1 R sig. Close that guy. Plus GM2 all over negative GM1 plus SCGD1. And this guy is multiplied by VY. So I want to take a second here to look at what we have. When we get this into our transfer function, right, where overall, just as a quick side note, I'm going to scroll up and write this down because it may not be intuitively obvious here, but our voltage gain for this system, AV, is going to be V out over VY multiplied by Vy over Vx multiplied by Vx over Vn. We have this stage taken care of here. So if we were to take the reciprocal of this part here, we can easily see that the denominator now, because we haven't flipped it over, is going to give us the location of our 0. And the numerator is going to give us the location of 2 poles. And we have a second order polynomial system. So we can literally just assign, we can say that everything, we're going to have AS squared, excuse me, that does not look like AS squared. AS squared plus BS plus C. If we set this equal to 0, then our pole frequencies, omega P1 is going to be equal to negative B plus the square root of B squared minus 4AC all over 2A. And omega P2 is going to be equal to negative B minus the square root of B squared minus 4AC all over 2A. And I'm just going to go ahead and put an absolute value sign around this guy as well, since these frequencies may wind up being negative. I wanted to do that now because when we get our Vy and V out relationship, if we multiplied things through, we would have a third order polynomial, and taking the finding the roots of the third order polynomial would either involve us having to suffer through applying the rational roots theorem and then doing synthetic division with this horrifying thing, or using the cubic formula, which involves taking the square root, taking the cubic root of complex numbers, which in my opinion is even harder. Since I know directly that we're going to be multiplying something through that has the well-defined root, it makes sense to take a moment here and see that we can get our 2 poles from this. So I just wanted to mention that. While we're at it, our 0 is going to occur at, you know what, I'll hold on to this actually. I'll hold on to the 0 for just a minute. All right, so we have our Vy over Vn relationship. Now we're going to do KCL at our output. This one's going to be a little bit easier. So if we look here, we're going to have V out divided by the impedance of the resistor, V out divided by the impedance of the capacitor C out, and then added to that will be GM times VGS2. So nothing too crazy there. So this is going to look like S C out V out plus V out over RD minus GM2 Vy is equal to 0. And rearranging things slightly, we're going to have 1 over RD plus SC out multiplied by V out is equal to GM Vy. And from this, we can see that V out over Vy, our last transfer function, is going to be GM2 times RD. Actually, let me go back one step to make this a little bit easier to follow algebraically. This tells us that Vy is 1 over GM2 RD plus S C out over GM2 V out. And now if I multiply my right hand expression by RD over RD, I get V out over Vy is equal to 1 plus SC out RD. Sorry, that's upside down. GM2 RD divided by 1 plus S C out RD. So if I multiplied these transfer functions together, I just want to be clear. If I multiplied all my transfer functions together, well, actually, before we do that, sorry, I'm kind of jumping around here. And I noticed something that I didn't notice last night when I was making out these notes. We could see that we're going to have a third pole that is simply at 1 over C out RD. And multiplying our transfer functions together, so multiplying this guy by Vy over Vn, we are going to wind up with something that looks like this. V out over Vn is equal to negative GM1 GM2 RD, which is the mid-band gain of our system. So this guy right here is AM. Oh, actually, I should do it over the top. Times 1 minus S CGD1 over GM2 divided by, I don't want to call this A, so we'll say 1 plus S over omega P1 times 1 plus S over omega P2 times 1 plus S over omega P3, where we've already defined all of our pole frequencies, which finally gives us a 0 then omega Z of GM2 over CGD1. So this was a lot of work to get results. So much so that I couldn't find this derivation in any of the transistor textbooks that I own. They all just say, that seems hard, let's use the Miller approximation. But this is a more direct and obviously then more correct response. We've been able to find out exactly what all three of our pole frequencies are, and we have found our 0. So this is going to give us a better picture of a response than any approximation. When we do the Miller approximation in just a moment, we are going to obviously lose our 0 for sure. And we are also going to see that we're only going to have, we'll still wind up with 3 pole frequencies as well, but they're just going to be a 4, or not necessarily a 4, but an approximation of these 2 guys that we have up here, omega P1 and omega P2. All right, so if we apply Miller's theorem, our small signal model would change slightly, right? Where that feedback capacitance CGD1 is going to be split up. So I'm just going to redraw that real quick. GM VGS2 RD. We have C out is still going to be equal to CGD2 plus CDB2. Here is V out. Down here, we'll have GM1, VGS1, and I'm going to call this guy CY prime because it's different than the CY that we had a minute ago, and we'll talk about what goes into it momentarily. And we're going to have this guy right here, which I'll call CX prime, over which VGS1 falls. Then we have our SIG, and here is VN, and here is ground. So CX prime, if we look at our original small signal model, gosh, 3 pages ago or whatever, what we've done is we've applied Miller's theorem to break this capacitance CGD1 into 2 capacitances falling between node X and ground. So we're going to see that part of it is in parallel with CGS1 and the other part of it is in parallel with CY. Okay? Yes?
Like after you have RD and C out.
They should be. Oh, I may have, okay. You're 100% correct. Yeah. So that is a mistake. This is correct. Thank you for that. I actually have that drawn that way in my notes. I don't know why I made that mistake. Thank you very much for pointing that out, because that would have made things very wrong and much harder to deal with. So Cx prime is just going to be CGS1 plus 1 minus, I'm going to just call this for now, AVXY times CGD1, because we don't know what the voltage gain relationship between node X and node Y is, right? We're going to do that next. CY prime is going to be CDB1 plus CSB2 plus CGS2 plus 1 minus 1 over AVXY times that same capacitance, CGD1. So let us now determine AVXY. All right. So with no capacitances mucking up our circuit, we have the following circuit. That's fair. Here is node Y. And here is our voltage, which would occur at node X. And then this is a bias voltage, V bias. So we are, just to be clear, still neglecting channel length modulation. So what we have here is our input is applied at our gate, our output signal is taken at our drain. This is a common emitter amplifier loaded with whatever resistance we see in this direction, right? Because channel length modulation is ignored. Otherwise, it would be R01 in parallel with whatever we see looking up. So our question then is, what do we see when we look up through that network? So if I draw my small signal model again, just real quick. Just focusing on that portion. GM2, VGS2. Here's RD. Here's the out. This is the terminal that I'm looking in at. If I applied some test voltage, Vx, and called this Ix, what resistance would I see? The current flowing in, what resistance would I see? So Ix has to be negative GM2 VGS2, right? Can't be anything else because all of this current can't flow through that open circuit, so it has to be flowing down through our test voltage source. So Ix is GM2 over VGS2, so let's write that down. Negative GM2 VGS2. Well, Vx is the potential difference between this node and ground, or the same thing as negative VGS2. Which means our resistance looking up from node Y, so I'm just going to call this guy R up, is simply 1 over GM2. All right. From that, our voltage gain AVXY is negative GM1 times 1 over GM2 is just negative GM1 over GM2, which gives us Cx prime is now going to be CGS1 plus 1 plus GM1 over GM2, CGD1, and CY prime is CDB1 plus CSB2 plus CGS2 plus 1 plus GM2 over GM1 times CGD1. All right. So we know what CX and CY are in terms of our circuit's parameters and all that kind of stuff. So let's take another quick peek at this small signal model. We have now no capacitor interaction whatsoever, right? All of our capacitors have been split up. No capacitor is influencing the behavior of another capacitor. So we can easily just now associate poles with particular nodes and have a pretty good approximation of what's going on. So we will have a pole that occurs with node X, a pole that occurs with node Y here, and a pole that occurs with the output voltage. So let me just label these real quick: X, Y, and output. So what does the capacitor, excuse me, what resistance does the capacitor CX prime see? Not a trick question. So if we're doing this, we're effectively taking the Thevenin resistance as seen by this particular capacitor, which means we would zero out our input voltage. So CX is directly in parallel with R sig. That's the only thing that it would see, right? And VGS, yeah, so let's just leave it at that. That's correct, so let's just leave it at that. So from this, the location of our first pole, omega px, would be 1 over CX prime R sig, which looks like R sig times CGS1 plus 1 plus GM1 over GM2 times CGD1, close parentheses, and there we go. So that's our first pole. What does CY prime see? Now we're making an assumption here to be clear, sorry, brain work there. We're effectively applying the method of open circuit time constants, which means CX prime is an open circuit and C out is an open circuit as well. So the only thing that CY prime sees is what's up here, which we just found a moment ago to be 1 over GM2. Giving us a pole omega py is equal to 1 over CY prime divided by GM2, sorry, GM2, not GM squared. Which looks, dang it, I have to do this thing, save, close, reopen. So it's going to look like GM2 divided by CDB1 plus CSB1 plus CGS2 plus 1 plus GM2 over GM1 CGD1. Lastly, we have our pole that will be associated with our output node, omega P out, And C out obviously just sees RD. So we have 1 over C out times RD, which is 1 over CGD2 plus CDB2 times RD. And if we had applied the method of open circuit time constants directly to this, we would have gotten the exact same results. So we could simply really add all these pole frequencies together, and the lowest one is going to be what the approximation for where the midband gain ends. All right. The very last thing that I want to talk about then, unless anybody has any questions about the Miller method that we just used to solve that guy, let me go back. Yeah. Those are our 3 poles that we found using the Miller method. Everybody else okay with me jumping to the next page? All right. So our very last topic then, which we are not going to spend more than 2 or 3 minutes on, is a differential amplifier. So a differential amplifier at high frequencies specifically is going to look something like this. Label this guy as M1. ISS. EGS2, this is VN2, this is VN1, CDB1, 1, V-out2, CDB, and up here is obviously VDD. So we could still analyze this guy using a half circuit method. Our half circuit becomes this. So that would be V out 1. This would be the in 1. Here's CGD1, here's CGS1, this is M1, this is CDB1, and we can see that our half circuit looks exactly like the common emitter amplifier that we started all of this high and low frequency analysis with, so I'm not going to bother doing that again because we spent like 2.5 days on it. All right, so that wraps up our frequency response of transistor amplifier sections. The textbook largely focused on BJT, so I decided to do CMOS so that between me and the textbook, you have a pretty good idea of what's going on for any type of transistor amplifier that you might be stuck with designing or analyzing, etc. Unless anybody has any questions, we're going to wrap up for today. I'm going to pop upstairs, again, finish grading that one last test, and then post your exam grades on Moodle before my class at 11. On Monday, we're going to kick things off on chapter, I think it's 12, on like feedback and stuff like that. I will just give you fair warning. That is probably the material that I am the least comfortable with out of all of this stuff. So we might go kind of slow because I'm trying to wrap my head around it too. Another thing that I wanted to just mention real quick, next Friday is the Senior Design Expo. So I'm going to be asking roughly 4 of you guys. We're not going to have class that day because I'm going to be in meetings from 8 a.m. until pretty much 4 p.m. But I'm going to ask 4 of you guys to come to speak with the Industrial Advisory Board, just because they like to talk to some of the upcoming seniors as well as the graduating seniors about what you think about the program and all that kind of good stuff. So for a couple of you guys, I'm going to send you an email just asking you to come talk to them for maybe half an hour or so at around, I think, 10:30. So yeah. No, I think it'll be at 11. I don't know. I don't remember what the agenda says, but I'll send you an email with the location and the time and all that kind of good stuff. And if you don't want to do it, just tell me and I'll find somebody else. All right. Thank you guys. See you on Monday.
Dr. Hahn,
Yes.
when we will get our grades for the exam?
Apparently you're not listening at all. I have 1 test left to grade. So I'm going to go grade that and then post your grades for the exam. So they should be up within the next 20 minutes.
Thank you very much.
Yep.
Have a good day.